Welcome to this first tutorial video for the course Intermediate Microeconomics. Today we will discuss a couple of exercises from the book from chapters 3 and 4 dealing with preferences and utility. The introduction, the appetizer to this video, was shot by my son Arnoud, who used all his creativity and all his Playmobil to give you an impression about what it means to make trade-offs in life, in this case between apples and bananas. Let's start with exercise 3.1. And the objective of 3.1 is to give you some insights about the exact relation between the marginal rate of substitution on the one hand and the convexity of indifference curves on the other hand. And we will do so by running through a couple of utility functions, seeing what the marginal rate of substitution is, and then also seeing whether the indifference curves of that utility function are convex or not. So let's get started. And for these tutorials online, I will use my tablet. And let's see how that goes. So exercise 3.1. And first we need to come up with the definition of the marginal rate of substitution. And if you see me looking down, then I will just write something down on the tablet, which then appears here on screen. And I hope that this will all be very readable. So the marginal rate of substitution between two goods x and y is the slope of the indifference curve at a certain utility level u1. So it's actually the negative of the slope. So we add a minus sign, then we take the slope, and to denote that it's the slope of an indifference curve associated with utility level u bar 1, we write u bar 1. And u bar 1 is just a number, a value. And this marginal rate of substitution is identical to the marginal utility of an additional unit of good x. So the derivative of the utility function with respect to x divided by the derivative of that same utility function with respect to the other good, which is on the y-axis, good y. So divided by uy. So the marginal rate of substitution tells you how many units of good y you're willing to give up in order to get one additional unit of good x. So, for example, if the value is 3, it means that the marginal utility of an extra unit of x is 3 times the utility that you give up by giving up 1 unit of good y. So let's do some examples. And the first utility function that we will consider is the following. So it's u, and it's a function of 2 goods. So that's easy. And it's equal to 3x plus y. Now, the first thing that we do is try to make a picture of the indifference curves associated with this utility function. And the best way to do it is to solve this equation for y, because y is on the y-axis and we want to express y as a function of x and the utility value that is associated with the indifference curve. So we rewrite it with y on the left-hand side, and we get that y in this case is equal to u bar, our utility level, minus 3x. And that expression allows us to graph the indifference curves. So we will go to this one over here, and I already graphed 2 indifference curves for you. So you can see that the slope is equal to minus 3. So we had y is u bar minus 3x. And if we have x equal to 0 and y is equal to 1, so we're at the point over here, and we plug in the values y is 1 and x is 0 over here, then it follows that if this one is 0 and this one is 1, it means that that point is associated with an indifference curve that has that gives a utility equal to 1. So u bar needs to be equal to 1. So here our green line that is closest to the origin is the indifference curve associated with a utility level equal to 1. And then I've also graphed a second one, a higher indifference curve associated with a higher utility level. And that's the one where our utility is equal to 2. And you can see that at these indifference curves, the person is willing to give up 3 units of good y. So let's make this a little bit larger. Let's erase. Oops. It's a bit too much. So the slope of these indifference curves is constant, and the slope is equal to minus 3. So it means that the individual is willing to give up 3 units of good y in order to get 1 additional unit of good x. So the marginal rate of substitution of this utility function is equal to 3. Now we can also do that a little bit more formally. So the marginal rate of substitution is identical to the partial derivative of our utility function with respect to x divided by the partial derivative with respect to y. And in this case we have that, given the utility function that we start out with, if we take the derivative of this thing with respect to x, then the derivative gives a value of 3. And if we take the derivative with respect to y, we end up with 1. So this one is equal to 3 over 1 is equal to 3. And again, this is identical to minus the slope of the indifference curves. So the marginal rate of substitution is not a function of x or y. So it means that it doesn't matter on which point of an indifference curve we are. At this point, the slope is equal to 3. Also, at the point over here, the slope is equal to 3. Here it's equal to 3. So the marginal rate of substitution is constant here. And the question is, whether the indifference curve are convex. It asks whether the marginal rate of substitution declines as x increases. Well, we know for this one that if x increases, the marginal rate of substitution doesn't decrease, it doesn't decline, but it stays constant. But these indifference curves are not strictly convex, but they are weakly convex. So this is the example where you have perfect substitutes, and in the situation of perfect substitutes, we have weakly convex indifference curves and a marginal rate of substitution which is constant. So that's the first exercise, first utility function. And now at question B, we have a second utility function, and you will recognize that one as the familiar Cobb-Douglas utility function. So In exercise B, our utility function is u xy is the square root xy. Again, to graph the indifference curves, we will solve this for y. So suppose we have on the left-hand side a number, so a utility value associated with a given indifference curve. And now we solve for y, so we bring y to the left-hand side. So we say, okay, this one is fixed at a level u bar. Then we have that the square root of y is identical to u bar divided by the square root of x. And taking the squares of the left-hand side and the right-hand side, we have that y is equal to u bar squared divided by x. And with that expression, we can draw the indifference curves because we plug in an x here on the right-hand side. So we plug in an x here. We just take an indifference level u bar, and what we will get out is the value of y. Now I've done so in this graph over here. So for example, if you plug in a value of, now first suppose that we fix the u bar level. So we take we want to draw the indifference curve that's associated with a utility level of 10. So we take u bar equal to 10. Now, we should not make our life complicated in drawing these indifference curves. So if this one we take equal to 10, and we take the 10 squared is 100. So we now have, in drawing the indifference curve associated with utility level of 10, we know that the relation becomes 10 squared is 100 divided by x. And then we want to take some easy values of x, which also gives us easy values of y, to get some points on the indifference curve. So a natural candidate is to take x equal to 10, such that the right-hand side becomes 100 divided by 10 is equal to 10. So y is also equal to 10. That's our first point on the indifference curve. So the first point is x equal to 10 gives us y equal to 10. And that's the first point on our indifference curve. Now, second point, take x is equal to 4, then you get 100 divided by 4. So y needs to be equal to 25. And that gives us the second dot on the indifference curve, which is this one over here. It's very symmetric, so a third dot of the indifference curve first point would be where we have x is equal to 25, which would give us y equal to 4. And now we have 3 points on the indifference curve, and we can connect the dots to draw the indifference curve. So let's do so, and we get that the indifference curve looks more or less as follows. And you can see that this is really a convex indifference curve. We also see that if we move along the indifference curve, so if we increase the value of, move along the indifference curve in the direction where x increases, then y at the same time decreases. So we have a diminishing marginal rate of substitution here. So now let's do this in a formal way. So let's write down the marginal rate of substitution. So the marginal rate of substitution, MRS, derivative of the utility function with respect to x, and then the partial derivative with respect to y. In this case, we get, so our utility function is equal to the square root of x, y. So taking the derivative of this expression with respect to x gives us, So it gives us 1/2 the square root of y divided by x, in both terms within the square root term. And if we take the derivative of the same expression with respect to y, we get 1/2 the square root of x divided by y. Now we can simplify this because the 1/2s, they cancel out, and we are left with y divided by x. And again, this one is diminishing in x, so if x increases, then the y does decrease. Now, what does the diminishing marginal rate of substitution say? So it simply says that if you increase the number of units of x that you already have at a given indifference curve, the number of units of y that you're willing to give up to get even more x decreases. So at this point, if, for example, we are here at the point 425, then you're willing to give up quite some y in order to get extra units of x. So delta y here is relatively large compared to the delta x. But if you move along the indifference curve, increasing the number of units of x that you already have, and you, for example, arrive at the point where you have already 25 units of x, then you're willing to give up only very little of y in order to get extra units of x. And that's the diminishing marginal rate of substitution. So what we did here is we said, okay, if there's a diminishing marginal rate of substitution, then the indifference curve is convex. Well, the picture clearly shows that. But that relation is sometimes a bit shaky, as we will see it in one of the next examples. And one condition that is always crystal clear is that when the utility function is quasi-concave, then the indifference curve is always convex. But that's a more advanced technical condition. You can find it in footnote 6 in page, I think, 98 or something. So, well, the condition is given in footnote 7 at page 100. And, well, let's do that one for this example as well, in order to give you the comparison between the two. So that condition says that a function u x y is quasi-concave if the following condition holds. So, and that condition is that the second derivative with respect to x times the first derivative with respect to y squared minus 2 times the cross derivative times the first derivative with respect to x times the first derivative with respect to y plus the second derivative with respect to y times the first derivative of the utility function with respect to x squared, that entire expression is smaller than 0. So that one should be negative. So get rid of that one. If this condition holds, then we know that the utility function must be quasi-concave, because that's the definition that follows from quasi-concavity. And then we also know that the associated indifference curves must be convex. Now, in The second exercise, we observed that we had convex indifference curves, so the underlying utility function must also be quasi-concave. So this condition must also hold. And this is what we're going to check. Now that looks daunting, but in practice it's just tedious bookkeeping, because our utility function uxy is equal to square root x square root y. That's the utility function that is given. So we know that if we take the derivative of this function with respect to x, we get 1/2 times the square root of At first sight, checking this condition may look daunting to you, but it comes down to simple bookkeeping. So what we will do is that we will check for each term on the left-hand side whether that one is negative, and if all terms on the left-hand side are negative, then this condition must hold, then the entire term must be negative. So we will start with the basics. Our utility function is equal to the square root of x times y, or you could also say x to the power 1/2 y to the power 1/2. And what we will do is to compute the derivative of this utility function with respect to x, to y, the second derivative with respect to x and y, and the cross partial. So start with the familiar. We take the derivative of our utility function with respect to x, which is equal to 1/2 x to the power minus 1/2 y to the power 1/2. Then we need to compute the second derivative. So we will take our result for the first derivative and take the derivative of that function with respect to x again. So doing that, we multiply 1/2 times minus 1/2, which gives you minus 1/4, x to the power minus 1/2, y to the power 1/2. Similarly, we take the derivative of the utility function with respect to y, and we get 1/2 x to the power 1/2 y to the power minus 1/2. And taking the second derivative, we get uyy is, again, 1/2 times minus 1/2 is minus 1/4. X to the power 1/2 y to the power minus 1/2. And then finally we need to compute the cross partial derivative. Now to that end, what you can do is you just take, for example, the first derivative with respect to x. So we take this one over here, and we take of that one the derivative with respect to y. And doing that, we arrive at 1/4, because we now multiply 1/2. That's already in front of here, in front of this one, times the 1/2 here. That's 1/4. So we get 1/4 x to the power minus 1/2 y to the power minus 1/2. Now we've computed all the elements that appear in the equation within the red squared bracket. And And now we can easily check whether the condition is satisfied and whether the utility function is quasi-concave. So we know that the x and y, they denote units, so they never can be negative. So we know that the partial derivative of u with respect to x, so it's multiplied plus 1/2 times something that is never negative. So we know that this thing is smaller or equal than 0, and we assume that both x and y are consumed in positive quantities. So this one is strictly, and I should not do it wrong, of course. So, yeah. 1/2 is positive. The x to the power minus 1/2, y to the power 1/2 is never negative. So this one is at least equal to 0. So this is non-negative. The second derivative with respect to x. So again, we have a term with x to the power minus 1.5, y to the power 1/2, which is non-negative, but it's multiplied with minus 1/4, which is negative for sure. So this entire thing is smaller than 0. The first derivative with respect to y is non-negative. Then the second derivative with respect to y is non-positive. And the cross partial, again, we have 1/4, which is positive, and then a term in x and y, which cannot be negative. So this one is positive. Now then, knowing all that, we can check the equation. So for the first term, we know that the uxx is negative. It's multiplied by a utility value that is squared. So this one is positive, but the sum of the two must be smaller, or the multiplication of the two must be smaller than 0. Then in the second term, we have two elements, ux and uy, that are non-negative. And also the cross partial is non-negative, but it's multiplied with minus 2. So the entire second term must be non-positive. And then the third term, we have the second derivative with respect to y. So that part is non-positive. And the second term is non-negative because we square something. So also the third term is strictly negative. And from this it follows that the condition holds. So this utility function, square root xy, which is a Cobb-Douglas utility function, is a is quasi-concave utility function, which leads to convex indifference curves. And that is the end of exercise B. So then continue with exercise 3. And exercise 3 gives you the utility function, and let's write it down, u xi is equal to square root of x plus y. Now again, we fix a utility value in order to be on one unique indifference curve. So we fix again the utility function at the value u bar, and we rewrite this equation solving for y. In this case, it's pretty simple. So y is equal to u bar minus the square root of x. And if we draw this indifference curve, we need to assume one indifference curve, so we need to fix a utility level, and let's fix our utility level at 10. Now then, if we plug in a value x is equal to 0, then the associated y value is equal to 10. So we are at the intersection with the y-axis at the value of 10, which is the green dot that's given here. Then we plug in another value of x, for example, 25. Why 25? Because the square root of 25 is equal to 5. And we have 10 minus 5 is equal to 5. So on the same indifference curve is the bundle which gives us 25 of x and 5 of y. Now if we have 100 units of x and no units of y, then our utility level will also be 10. So that point is also on this indifference curve. And if we connect the dots, we get an indifference curve that looks as follows. So this is the indifference curve associated with a utility level of 10. Now we will make less work of this exercise than of the previous one, so we will not check for quasi-concavity, but we will only look at the marginal rate of substitution. And so the indifference curve, the graph already shows you that the indifference curve is nicely convex, so that is fine. But let's compute the marginal rate of substitution. So marginal rate of substitution by definition is the ratio of the derivative of the utility function with respect to x divided by the derivative with respect to y. Taking the derivative with respect to x, we get 1/2 x to the power minus 1/2. And taking the derivative with respect to y, we arrive at a simple 1, because there was nothing in front of the y term. And, well, another way to write this is 1 over 2 times the square root of x. And again, from the graph, you can see that nicely, if we move along this indifference curve, so if we go from the point over here to the point over here, so that means that x is increasing, at the same time y is decreasing, and the slope is decreasing as well. So the marginal rate of substitution is diminishing. That's exercise C. And we continue with question 3.1d. At this point, you may wonder, okay, I already solved a couple of them. Why do one more? Does it have added value in the sense that I learn anything new? The answer is yes, you will learn something new from this one because it's a different situation. On the other hand, this is also quite a bit of a tedious exercise because we need to do quite a bit of derivation here. So, and the utility function that is given is the following. U x y is the square root of x squared minus y squared. And first, we're going to draw a picture of one indifference curve to see what actually we are looking at. So, and what we will do is we will solve this equation, this utility function for y. So we fix the left-hand side at a specific value of utility in order to get one indifference curve, and we take the indifference curve associated with a utility level of u bar. And then we solve for y. So we get, if we take the square of the left-hand side and the right-hand side, we get that y squared is equal to x squared minus bar u squared. So y is identical to the square root of x squared minus u bar square. And now we can take one indifference curve here, and let's take the one associated with utility of 10. This is not without reason that I take this value, because it is a nice value to take. So let's draw the indifference curve associated with utility level of 10. And we will see that if I take x also equal to 10, then x squared will be 100 minus u bar square is 100, so y is equal to 0. So my first point on this indifference curve will be the point 10, 0. So that's the one over here. And then I could also ask, okay, what if my consumption of x is equal to 15? What is then the corresponding consumption of y? Well, if I take 15 squared, it's 225 minus 10 squared is 100. So it's 125. And I take the square root of 125, which is about 11.80. So the second point on my indifference curve is about here. And now you can also do the intermediate values, but the indifference curve associated with utility of 10 looks something like this. And here you can see something remarkable, because if my consumption of x is increasing, then also my consumption of y is increasing. And the reason for that is that in this exercise, good y is so-called bad. We don't really like it, but we want to have more of y if, as compensation, we are also given more units of x. So, and it also shows from the y squared entering the utility function with a negative sign. So the more of y we get, the lower our utility, or in order to stay on the same indifference curve, we need to be compensated with more units of x. Okay, so and then the marginal rate of substitution. In this case, well, we just take the derivative of our utility function with respect to x and divide by the utility function derivative with respect to y. So let's do that. So marginal rate of substitution is ux over uy. And taking the derivative with respect to x. Now, the derivative of the thing within the square root is 2 times x. So we get that placed in front of it. Then we multiply with 1/2 because the square root is to the power 1/2. And the power gets diminished by 1. So the original square root of 1/2, we subtract 1, the new power becomes minus 1/2. And also taking the derivative of our utility function with respect to y, we get a similar expression, 2y times 1/2 x squared y squared to the power minus 1/2. But of course, notice that here in our utility function we have a minus sign, so the derivative of minus y squared is minus 2y. So we have a minus sign here as well. And we can simplify this a little bit, because some of the terms, they get cancelled out. The 2's, they get cancelled out. The 1/2, they get cancelled out. And everything is reduced to minus x to the power 2 minus y to the power 2 to the power minus 1/2 y x to the power 2 y to the power 2 to the power minus 1/2. And of course also the term, the final term, they cancel out. So in fact the marginal rate of substitution is minus x divided by y. And now you need to pay attention, because the question then is the marginal rate of substitution diminishing? So what we had before, for example in this graph, is that if you move in the direction of increasing x, then the slope of the indifference curve becomes less negative. So we get from very negative to less negative. But in this case, what we have is an indifference curve where the slope is positive and it becomes less positive. So we don't have a diminishing marginal rate of substitution, but actually an increasing marginal rate of substitution, because the marginal rate of substitution is the negative of the slope. So and if the slope goes from very positive to less positive, then the marginal rate of substitution is not diminishing. And you may easily come to the wrong conclusion, because if you would just look at the marginal rate of substitution, the expression that's given here, you say, oh, if I increase x, then this thing, the numerator becomes larger, times a minus sign, so this entire thing becomes more negative. However, in this case, it doesn't hold, because if we increase x and we move along the same indifference curve, also the y increases. So, in fact, what happens is that this thing becomes larger. So, and larger means that it becomes less negative. So, for example, if we are over here at this point, then it's very steep. So x is equal to 0 and y is equal to, or x is equal to 10 and y is equal to 0. So here it's the slope is plus infinite, and the rate of marginal substitution is actually minus infinite. And if we then increase x and we also increase y, then actually this thing becomes less positive and the marginal rate of substitution becomes less negative. And that's exactly the flip side of a diminishing marginal rate of substitution. Actually, we have an increasing marginal rate of substitution. Okay, and this is all because good y is a bad. So our willingness to accept more of the bad declines in x. So the more x we have, if you want to give us an additional y, the more additional x that we would need as compensation. Okay, so the marginal rate of substitution is not diminishing, but then the remaining question is, are the indifference curves convex? And that is the case. So you can already see it from the indifference curve that we drew. That clearly this thing over here, this indifference curve, is convex, but we need to prove it. So in order to prove it, we will use the definition that is given, and we will compute all the terms. And this is the tedious part of the exercise. So let's get done with that. And I will repeat the utility function. So square root x squared minus y squared. And what we now need to do is that we just plug in all the terms of this expression. So first we take the derivative of the utility function with respect to x, which is x over the square root of x squared minus y squared. And this thing is positive, or at least it is non-negative, because the value of x is never negative. And then we take the derivative of the utility function with respect to y. So that is minus y over the same term, square root of x squared minus y squared. This thing clearly is never positive. So the marginal utility of y is always negative, and this is because good y is bad. And now we take the second derivative with respect to x, so meaning taking the derivative of this thing over here. So now we use the quotient rule. So we take the denominator and then the derivative of the numerator. Well, the derivative of the numerator is easy because the numerator is x, so the derivative of that thing is 1. So we get 1 times the denominator as our first term. So we get square root x squared minus y squared. And then we get the derivative of the denominator, which is the more complicated thing, times the numerator. Now the numerator is equal to x, and the derivative of the denominator is equal to 1/2 2x divided by the square root x squared minus y squared. And then we divide by the denominator squared. Now, in the denominator we have a square root. That one disappears if we take the square. So we have x squared minus y squared. And we can simplify this a little bit, because the 1/2 and the 2's, they again cancel out. And we have this expression over here. And then we can simplify this further by breaking out the square root. So we can rewrite this as 1 over the square root of x squared minus y squared times 1 minus x squared over x squared minus y squared. And I should show this here as well. So you can see that the first term, if we take this part, just if you have the square root of 2 and you divide by 2, then the result is 1 over the square root of 2. So that's the first term that we have over here. And then the second term is that, well, we just break out this thing over here. So and now I see that here I forgot something, because here we have 2 times x and here we have x. So we should also add a square here in order to get the square over here. And now then we can do the same for the second derivative of y. So we get y is identical to minus 1 over x squared minus y squared, 1 plus y squared x squared minus y squared. Sorry for the handwriting here. And then we have the cross term, so the uxy. So we can get that by, for example, taking derivative of the derivative with respect to x with respect to y. And if we do that, then we get xy over x squared minus y squared to the power 1.5. Okay, and now we are ready to combine all the stuff, which is the complicated thing to do, especially solving for it. So we get back to this equation over here, and we combine all the terms. So, and we have three parts, and I will refer to them as the green part, and let's do well, the orange part, that's the second term, and then the red part, which is then the final term of this expression, and we will go by them one by one. So let's start with the green part. Let's do that over here. So the green part is uxx uy squared, and that part is identical to y squared over x squared minus y squared to the power 1.5 times 1 minus x squared minus y squared. So, and this is because we have the second derivative with respect to x, which you had written like this, and then the derivative with respect to y squared, which gives us y squared divided by x squared over y squared. So an x squared over y, x squared minus y squared. Yeah, so the green part is actually, I should write with arrows because otherwise you don't know what I'm pointing at. But we take this part squared, which is y squared over x squared minus y squared, times this form over here, which is another x squared minus y squared to the power 1/2, times this part over here, and we arrive at the equation that we have over here with the y squared x squared minus y squared to the power 1.5 times the original term within parentheses. Okay, so that's the first term. Then we have the second term. Oops. And the second term is minus, maybe I should make it a little bit bigger here. So we have minus 2 times the cross term times the first derivative with respect to x and the first derivative with respect to y. So we have minus, and then we have 2 times xy divided by xy of x squared minus y squared to the power 1.5 times the derivative with respect to x, which is x over square root x squared minus y squared times the derivative with respect to y, which is minus y, and then the same term in the denominator. And we close the parentheses here. That's our second term. And then we have the third term, which is the red one. So the red one is the second derivative with respect to y times the first derivative with respect to x squared. So we have plus uyy ux squared, and this gives us minus 1 over x squared minus y squared times 1 plus y x squared minus y squared times x squared minus y squared. And now we can simplify. So now we have this entire expression, and we have a lot of the same terms, x squared minus y squared, so we can simplify quite a bit, and I will guide you through. So first, starting with the green part. So this part over here will become equal, so we just leave the y squared where it is. And now we have, so what you observe is this is identical if we multiply the one, both the numerator and the denominator, with x squared minus y squared. So, and then we have x squared minus y squared. If you do it like this, then you see that this is identical because the x squared, they cancel out. So this one is identical to minus y squared, x squared minus y squared. And then we can bring this x squared minus y squared, that is the same as this one over here. So we can rewrite this entire thing over here as y squared, which is the part that is over here, divided by x squared minus y squared to the power 2.5 times minus y squared, because that's the part that is left over here. So that's the simplification of the first part. Then we can also simplify the yellow part, and actually this is easier because these are 3 multiplications, so we can simply multiply the first part with the second part in the third part, and then we have a minus sign over here and a minus sign over here. So here a minus and there a minus, so together that becomes a plus. So we have plus 2 times x squared y squared divided by x squared minus y squared to the power 2.5. And then we have the final part, the red part, where we can apply a similar trick as before in the first part, noting that the term within parentheses is identical to x squared over x squared minus y squared. So, and knowing that, we can wrap all the terms together, and we get minus x squared minus y squared to the power 2.5 times x squared. Okay, now we are almost there. So we did a number of reductions. So forget about the things to the left here. And what you see is in the first term, the denominator is x squared minus y squared to the power 2.5. Also in the second term over here, and also in the third term over here. So now we can easily wrap together all the elements in the numerators, and we arrive at minus y to the power 4 plus 2 times x squared y squared minus x to the power 4 divided by x squared minus y squared to the power 2.5. And we can further simplify this by noting that the numerator is identical to minus x squared minus y squared to the power 2 and divided by the same term x squared minus y squared to the power 2.5. We arrive at the final result that this expression is minus 1 over x squared minus y squared, which is negative. So we have that the utility function is quasi-concave. And as promised at the beginning, this is a tedious derivation in order to prove quasi-concavity, but in the end we made it. So congratulations to all of us, and this completes exercise 3.1d. Now then we have one more utility function to go, which is in question E. And question E is a utility function with a subsistence level, meaning that you have to consume at least a certain number of units of x in order to survive. So we have a utility function uxy is equal to xy divided by x plus y. And we, in order to draw the indifference curve, we want to solve this one for y, for a given utility level u bar. So what we will do is we will bring this part to the left-hand side, and we will again replace, so this one goes to the left-hand side. We fix the utility level at a level bar u, and we solve for y. So doing that, we get that x, so tablet is being slow. X plus y times bar u is xy. So in the second step, we have that x is equal, or y is equal to x times bar u divided by x minus bar u. But y can never be negative, so the denominator has to be non-negative. So we have to impose the additional condition that x has to be at least equal to bar u in order for this expression to make sense. Which brings us at the following indifference curve, taking the utility level u bar as given, and our indifference curve then has the following form. We have a vertical line, so x can never be smaller than this vertical line bar u, which is given here. And this is our indifference curve. So as long as x exceeds bar u, our indifference curve is given by this expression over here. So, but we can never reach that indifference level u bar by giving up all units of x and only consuming y. Also, when we would consume an infinity number of units of y, we still need at least bar u units of x in order to reach the utility level bar u. So what is then the marginal rate of substitution? In this case, the marginal rate of substitution is equal to the marginal rate of substitution, derivative of the utility function with respect to x divided by derivative with respect to y, and solving gives us x plus y minus x times y, and the derivative with respect to y is x plus y, x minus x times y. Now, then you can simplify, some terms cancel out, and finally you arrive at y over x squared. Now, clearly, here if you increase x, now then from this indifference curve that I showed you, if you increase x, the number of units of x, at the same time, when you move along the indifference curve, the number of units of y that you consume goes down. So the marginal rate of substitution, the numerator becomes smaller, this one gets larger, so the marginal rate of substitution is clearly diminishing, and we have a convex indifference curve. And that brings us to the end of exercise 1.